Hi everyone, welcome back to Dr. Tutor. Today we're starting on Chemistry Unit 3 for QCE, and the first topic is chemical equilibrium systems, but before we get started, don't forget to like and subscribe to get a good ATAR. So moving on, the first topic is chemical equilibrium systems, and the first section in that is chemical equilibrium. So there's a couple of things we need to talk about before we get on to what is chemical equilibrium, and the first thing is what is a chemical system? So a chemical system is a set of molecules, usually a chemical mixture with interacting molecules, and there's two types that you actually need to know. So the first one is an open system, and that involves like a container which is literally open, so it literally means open. So say you have some kind of solution in here. If you're like boiling it or like heating it up or something, then these particles can escape to the external environment. So that's why the system is kind of open, because the matter within it can be exchanged with the external surroundings. Also, keep in mind that the energy can be exchanged with the external surroundings. So, like, if you're heating this up, you can have that fire be underneath the technical system, and then that fire is still heating it up, so it's transferring energy between the system and the outside. The other type that you have is a closed system. So, in a closed system, I'm sure you can guess, it's like a container that's actually closed. So, say if you have the same situation where you have a lid on it, right? And then you have these molecules in here, you have the matter. The matter can no longer be exchanged with the external environment. So, if you're heating it up, right, then you won't be able to get any of these particles escaping. They're all just trapped in there. So that means that there's no matter exchange with the external environment. However, there is still energy exchange because it's pretty difficult to prevent like thermal energy, for example, from not spreading. So if you're heating it up, it would be like if you had like a pot on the stove with a lid on top of it, effectively. So to summarize, an open system allows matter and energy to be exchanged with the surroundings, and a closed system allows energy but not matter to be exchanged with the surroundings. This will be important later, so remember this. Okay, then the second thing that we need to know before we talk about what is equilibrium is physical versus chemical changes. So with physical changes, you have no bonds being broken or made. So that's like if you have an ice cube. I'm going to draw a really bad ice cube, and that turns into a cup of water. That would be considered a physical change, because in that situation, you still just have H2O molecules, but they're just like packed differently. And then as they melt, they're still H2O molecules, nothing's happening to the actual molecule, it's just changing its state, right? So that would be considered a physical change. Specifically, the atoms in the molecules stay the same, so they don't change the arrangement or the bonding of the actual atoms. So say this is like a H2O molecule, nothing happens to those bonds, but there's only change in terms of like the position or the spread or the movement of those molecules. So in a solid, we have our molecules really tightly packed together, whereas in the liquid state, we would have them kind of floating around a little bit and like moving around a little bit more. So that's like the changes that you get happening. Not any changes to the bonding or the chemical structure, just changes to like the physical properties, if that makes sense. Okay, so yeah, the main examples would be like melting or boiling or stuff like that. Okay, then the other type we have is chemical changes, which is when you actually change around the bonding of different molecules. So say if you have like another H2O molecule, an example of that would be like if this gets changed into an OH and a H, right? That would be considered a chemical change, because this time bonds are being broken or made, and there's a change in what we call the chemical composition, which basically just means that the molecules actually change identity, and now we have new molecules that we have like different names for. Some examples of that would be like combustion or single or double displacement. For example, in combustion, you have a hydrocarbon, which would be like CH4, and oxygen, which would be O2, react to form water and carbon dioxide when you heat them up. Combustion is basically just the name for when we like set things on fire. So that's what happens like when you have a candle, for example. Okay, so I balanced this equation now, and you can see that we actually see that this molecule, for example, the bonds in this molecule have broken apart. So these bonds are broken. And instead, this carbon will like go over here, and it'll like form new bonds with these oxygens. So that's the main thing that defines a chemical change, is like this idea of bonds being broken or made. So in a physical change, that doesn't happen, and in a chemical change, that does happen. The other important thing to know with these physical or chemical changes is whether or not they're reversible. So all physical changes pretty much are reversible. So for example, like if you have an ice cube and you melt it, you can just refreeze that water and it's fine. It doesn't really affect anything. With chemical changes, only some of them are reversible. So you have reversible chemical changes and irreversible chemical changes. Again, this will be important in a minute. So this brings us to equilibrium, where For reversible reactions, that can be physical reactions or reversible chemical reactions, there's a forward reaction where we go from products to reactants. So let me write that down here. So we have forward, which is products to reactants. And then we have a reverse reaction, which is just the opposite, so it's reactants to products. And the importance of having these two reactions is basically just so that like we can talk about the two things that are happening at the same time. It just helps us to give a name to what's going on. But it's important that you remember these because they do come up a lot. And what is happening in this situation is that the forward and the reverse reactions can occur at the same time. And what that would look like, if we go back to this ice cube example, is basically you have your ice cube, right? And you have your water. Let me put this in a cup as well. And what is happening is that the ice cube is turning into the water, and at the same time, the water is turning into an ice cube. So this is what you would see if it was at the freezing point, because in that situation, you would have some of the water freezing into ice, and some of the ice freezing or melting into water. And so we see that both the forward reaction and the reverse reaction are happening at the same time, and we have this special arrow that I've drawn here, and that's called an equilibrium arrow. Okay, so what is the official definition for this that you need to know for your exams? In a closed system, over time, physical changes and reversible chemical reactions reach a state of dynamic equilibrium. Okay, so the important words here is dynamic equilibrium. And what that basically means is that the forward reaction and the reverse reaction are occurring at the same rate. And what that means is that the concentration of products stays the same, and the concentration of reactants stays the same. And that's because for every little ice cube molecule that turns into a water molecule, which is technically the same molecule, but whatever, what basically happens is that at the same time, a little piece of water will also turn into a little piece of ice. So since the reactions are happening at the same rate, the product and the reactant concentrations, they always will stay the same. And we won't be able to notice any difference in like the size of the ice cube or the amount of water. Okay, then the next thing to know is that we can have something called an equilibrium position. So remember how I said, what if we have a cup of water with a little, like half an ice cube in there? We could have a different equilibrium system where we have the same cup of water, but we have less water and more ice. And so it always stays as like being more ice than water. Or we could also have a different equilibrium system where we have heaps of water and we just have like a little tiny bit of ice, right? And in each of these different systems, we wouldn't see the size of that ice cube increase or decrease because the reactions would be happening at the same rate. However, there is obviously a difference between these different equilibrium systems, right? Which is probably temperature related, but I'll come back to that in a second. And so we see that if there's consistently more product or consistently more reactant, we need a way to define what is the position of equilibrium. And so what we do is we say that if there's more product, then the equilibrium position would be closer to the product side, which is described as being to the right. So like if we think of this reaction, right, where we have reactant to product, which in this case is probably like ice cube to water, or I guess it could be water to ice cube as well, depends if you want to be silly or goofy. And so we can see that if we have more product, like say our reactant is the ice cube, then we would see that this first one here, this first example, that would probably be like right in the middle. So our equilibrium position would be right in the middle, right? But for maybe this one, we see that there's way more reactant. So we would say that the equilibrium position is shifted to the left because it's to the reactant side. And maybe for this one, we would say because there's way less reactant, way more product, we would say that this is shifted to the right because we're kind of favoring the product side. Okay, so moving on to the reversibility of these chemical reactions. They can be explained by considering the activation energies of the forward and reverse reactions. So what is activation energy? So there's energy initially in a chemical reaction required for two things. Number one is to start the bond breaking, but breaking the bonds actually releases energy. So there's always chemical potential energy stored within chemical bonds, but to kind of cause the initial breaking process, we need a little push of energy, and then after that, all of the bonds that break will release their energy for usage in the rest of the chemical reaction. The second reason why we need some activation energy is to start forming the new bonds, because obviously if bonds have chemical potential energy in them, we would need energy to be put into the bonds when they're getting created. Okay, so What that means is that activation energy, which is written as EA, is equal to the minimum energy required to break and form the bonds necessary for that chemical reaction to occur. So I'm just going to write minimum energy here for the reaction. Okay, so what that means is that we need this activation energy to start off the reaction. Okay, then we have this other thing, which is called enthalpy, which is written as delta H, and that's basically related to the change in energy of the system, okay? So both the forward and the reverse reactions are going to have a different activation energy, because if you think about it, there's technically different things happening, and different amounts of bonds being broken versus being made, and different types of bonds as well. So that means that they would have a different activation energy for the forward reaction, and then a different one for the reverse reaction. And that means that one of them is going to be exothermic, and one of them is going to be endothermic. So what do these words mean? So exothermic is releasing energy into the external environment. So remember, equilibrium can only happen in a closed system, because if we start having matter exchange with the external environment, then it's like it'll never reach equilibrium, because new molecules will keep getting introduced, or like the molecules in here will keep spreading out. So we have to have it happening in a closed system. And what that means is that we have no matter exchange, but we still do have energy exchange. So what that means, again, is we can have exothermic reactions or endothermic reactions, which in an exothermic reaction, we overall release extra energy as heat. So usually that would be like if the test tube feels hot, right? Then that would be because the reaction happening inside is actually releasing extra heat, and then your hand, as you're holding the test tube, absorbs that extra heat. And when we have that situation, we have a negative enthalpy, so we have negative delta H, because it's using up less energy than what is initially being put into it, so it has extra energy left over. The other type that we have is endothermic, which means it feels cold, and that is a positive delta H, and that happens when it overall is taking energy from the surroundings, and that's why it would feel cold in the test tube. Like if you're holding it, it'll feel cold because it's actually stealing the heat from your fingers in order to make the reaction happen, so it's a bit of a thief. Just to talk about these words quickly, thermic is like, thermal energy, thermals, like heat related, and then exo means like exiting, and endo is kind of like entering, so this is like exiting heat, and this one's like entering heat. Hopefully that helps you remember. Okay, so effectively what's happening in an equilibrium system is that one reaction keeps making energy, and the other keeps taking energy, so we overall kind of get to like this energy balance, and then that keeps happening in a state of equilibrium. However, like if we're starting off something, then we might need some activation energy. Okay, so let's take a look at a specific example, because sometimes you might be shown graphs relating to activation energy, so I just want you to have an idea of what that looks like. So here we've got a graph with energy on the y-axis and then time on the x-axis. And what we see happening here is that we've got our reactants, right? They're just sitting, they're just chilling, they just have a constant energy, nothing's happening to them yet. However, once they get kick-started with this reaction, we see that that energy increases up, and then it starts coming down. So what's actually happening here is that we're adding some energy into the system. That energy gets used to break bonds, which then adds like more energy into the system, because as those bonds break, they release the energy that they've been storing. And then all of that energy starts getting used up to create the new bonds. Okay, so this is like the progress of a chemical reaction, where we have the reactants just chilling, then we start adding energy, and then once it's got enough, it hits like this peak point, and then it starts coming down because that energy is getting used up to make the new bonds. And then once we're done, we just have the products sitting and chilling. Okay, so this amount of energy is our activation energy, because that is our minimum energy required for the reaction to actually continue to happen. If we only got up to here, for example, that wouldn't be enough energy to break all of the bonds or to form all of the new bonds. So we have to at least get up to this peak, right? And once we do, then the whole reaction kind of finishes off, right? Okay, then we have this other line, which is the enthalpy. And what that tells us is the difference in the like baseline energy of the reactants and the baseline energy of the products. And so that's our difference from reactants to products. And we can see it's gone down. That's why we have a negative delta H. And what that means is that it's exothermic, so it loses heat to the surroundings. So because it had more energy before, and now it has less energy, where did this extra energy go? It just like zoops away, basically. Alright, so this, for example, could be the forward reaction, which is exothermic. Then what that means is the reverse reaction is literally the exact opposite of that, but our activation energy and our enthalpy is different. So let's have a look. So again, this is the same graph. We have energy here and time here. Oh my god. we have energy here and time here. And then what happens is, again, we have our resting energy of the products. That should be exactly the same as this, because it's the same thing. And then we have our resting energy of the reactants. Again, that should be exactly the same as this. But the difference in this case is that our activation energy is a lot higher, because we have to go back the opposite way, right? So we need this much energy all the way from here to here to actually get the reaction to happen. And so we have that, it increases, it decreases down again. And then, now our change in energy from our reactants, or our products to our reactants actually, is positive, because we can see that the overall energy has gone up. And what that means is that, how did it get this extra energy? Well, it just stole it, because it's a little thief. And that means it's endothermic, so it gains heat from the surroundings. Okay, so if you're still confused about this activation energy thing, basically it's the amount of energy that is initially required to get to this peak, and then after that, it just uses up as much energy as it needs, but it might not use up all of the activation energy that was initially required. It is a little bit weird. Cope, I guess. Sorry. And then also just remember that this activation energy, some of it will be made up from the bonds of the, whatever's on this side. Because this has, some resting energy, right? That means that that's, the energy that's stored in the bond. So when that energy gets released, that kind of gets added to the activation energy as well. Okay, then the very last thing for this video is experimental data and graphical representations. So equilibrium graphs are drawn like this, with time on the x-axis. This is different to the activation energy graphs, by the way, because we have concentration on the y-axis. I'm just going to write that as this, or even just as C. Okay, so say on this graph, we have our concentration of products, and then we have our concentration of reactants here. And I'm not going to tell you why these graphs look like what they look like, because that would be spoilers for the next video. But what you need to know for now is that in equilibrium, because the concentration of products stays the same, and the concentration of reactants stays the same, that's the whole point of the equilibrium, is that the concentrations no longer change. What that means is that when we get to this point, where all of these lines plateau, and they're all flat, right, that indicates graphically that the concentrations aren't changing anymore. And so what that means is that at this point, the system is at equilibrium. So from this point onwards, we would say that the system is at equilibrium. Hopefully that all makes sense. In the next video, we're going to talk about factors that affect equilibrium and Le Chatelier's principle. And that's pretty much it. So leave a comment if you have any questions. And if you want a complete subject guide, you can go to the link below, or you can get an active ATAR membership, which gives you access to all educational content for all subjects with thousands of practice questions and also answer explanations. Or you can also directly book online tutoring and assignment help with that link as well. Anyway, please like, subscribe, and share this video to your friends, because it really helps get this content out to more people. And thank you for watching. Bye!